All right, last talk of the session, SOLAS Science and Environment Impacts of Marine Geoengineering. Cliff Law. All right.
Thank you, and thanks to the organisers for inviting me to talk. My talk is going to be a bit different from the others in this session today. It's not so much per se about a geoengineering technique, but more about the fundamental research that informs what we know about potential geoengineering and also about the role of the scientists, the science community, and the dilemmas that they face. I should point out this talk won't involve any audience participation, and there certainly won't be any weddings involved in this talk. So. Okay, so background to this. So I'm talking first of all about the SOLAS group. This is basically, it's an international pool of scientists with expertise in the ocean and atmosphere, but particularly how those two interact. This is basically, as I say, it's an international organisation. It has a range of sponsors, some of which are shown up here, formerly the IGBP, but now it's been replaced by the Future Earth, some other things like SCORE and the World Climate Research Programme. And basically it has a senior steering committee and an IPO that's run out of Kiel in Germany. And really they provide scientific guidance, development, planning and implementation. They decide where funding goes, the collaboration and interaction with the sponsors, and also publication and dissemination of results. The important thing to notice is an international organisation with 26 national networks and with about 2,500 scientists in 75 countries. So the science itself is really shown there in that statement there. It's really about understanding the key biogeochemical physical interactions and the feedbacks between the ocean and atmosphere and how that is affected by climate and environmental change. And this is a nice little graphic showing the different components of the work here, moving from down at the center of your screen, how greenhouse gases are affected by ocean processes, moving to the left about how the exchange, the physical mechanisms, then looking at things from the land like atmospheric deposition of things like dust and pollutants, and then getting into the atmosphere, how the marine system affects clouds and aerosol production, and then finally atmospheric chemistry. So to bring it round to what we're doing here about negative emissions, I mean, clearly some of this science has direct relevance to some of the marine negative emission technologies we've already heard about. And here's just a few examples. On the right-hand side of your screen there, you've got things where basically techniques that are talking about increasing the productivity of the ocean and therefore its ability to capture carbon. And so these are all things like maybe moving nutrients around, like in the upper picture, which is showing artificial upwelling through pipes. Then there's ocean fertilization. We've already heard about the deliberate addition of nutrients to the ocean. And then there's things at the bottom like macroalgal farming to increase carbon sequestration by seaweeds. On the left-hand side, you've got more deliberate attempts in terms of using the ocean as a storage of carbon. So you've got biomass storage. In this case, there's an example of using crop residue and sinking that in the deltas of estuaries where it can be stored for long term. There's increasing ocean alkalinity we've already heard about. And then there's things like deliberate and direct storage of CO2, both at the seabed and in subseabed storage. So just bringing this back to SOLAS, I pointed out to you that there's a number of themes within SOLAS, so just pick up on two of them and about how they connect with negative emissions. And so really this first one looks at about greenhouse gases in the ocean, really about how surface ocean processes control greenhouse gas cycling, both at regionals to global scales, and what are the feedback mechanisms between climate change and ocean greenhouse gas emissions. So in this we're talking not just about CO2, but N2O and methane as well. But also there's an important point about this work that we do is that we're providing it, or we're developing the logistical capability to actually assess these fluxes. So whether it's actual direct exchange of these gases or storage of these gases in the ocean, SOLAS is actually developing a network for monitoring these things. So you can see from some of these we've got like net-related issues. That SOLAS is looking at the baseline conditions in the ocean in terms of carbon. It's looking at the efficacy of how a particular negative emission technology in terms of how carbon cycling in the ocean might change that. But also we're concentrating on unanticipated impacts as well. Now, another theme, just to briefly mention this, is about atmospheric deposition of the ocean, and this is really about how the ecology and the biogeochemistry of the ocean responds to the deposition of both natural and anthropogenic materials. You've got things like volcanoes, dust, and pollutants, and biomass burning. And so what are the large-scale impacts of these processes on the global elemental cycles in the ocean? And so once again, we're looking at a net-related issue of this research is around the efficacy of this added material, whether it's in the form of dust or other materials, but also coming around to how carbon sequestration might be affected by nutrient enrichment in the ocean. And so this is where I want to give you an example of what SOLAS has actually been doing in this space and how it has informed the whole debate about geoengineering as a whole through this iron hypothesis. Now, this was already mentioned earlier in Phil Williamson's talk. And I should point out here that the driver for all this research that I'm going to talk about is to develop some fundamental understanding of the ocean, about why you've got areas of the ocean that have an excess of nutrients and the phytoplankton grow. The driver for this research is not geoengineering, but because of the information it's provided, it's more and more brought into this field. So basically, Phil mentioned earlier about the fact that this iron hypothesis grew from John Martin, a US marine biogeochemist, who basically realized that because there was this excess of nutrients in the surface ocean, what the phytoplankton were lacking was iron. You know, we all need iron. We have iron in our blood, in our hemoglobin, and equally phytoplankton need iron as well. But in some areas of the ocean, they're lacking in it. So if you increase the amount of this iron that's in the surface water, they will increase their uptake of nutrients and carbon dioxide. Then, obviously, we're used to the fact that most of this material that's through the phytoplankton goes into the food chain, is basically recycled back to carbon dioxide. But a small process of it, a small part of it, is transferred into the deep ocean. So by adding iron, if you increase this cycle here, you can actually increase this transfer into the deep ocean. And so there's evidence of this from all sorts of different scales, but I particularly like this one because it's evidence on a very long time scale over the paleo record from the Vostok ice core. So what you're looking at here is from now back 170, 1,000 years or so, showing the different glacial and interglacials. And what you're looking at there with those yellow arrows is showing that when iron is high, then carbon dioxide is low. So you've got, even in the paleo record, you've got some indication that iron availability is affecting atmospheric carbon dioxide. So John Martin was a pretty smart guy. He knew how to sell an idea, so he basically went out promoting this idea of doing deliberate iron addition in the ocean with the phrase, "Give me a tanker full of iron and I'll give you the next ice age." So obviously this attracted quite a lot of attention, and so for the next 10 to 15 years or so, there was about 12 of these iron addition experiments from about 1994. And you can see basically these experiments started off in the equatorial Pacific, then moved to the Southern Ocean, and then subsequently to the subarctic Pacific, with a few in the areas around the North Atlantic in association with phosphate addition. So just to tell you what one of these things is, this is like the framework of an iron addition experiment. The basic concept is you have a ship, you're delivering about 1 to 10 tons of dissolved iron into the surface water around the ship. You add this with a tracer so you can find out where the area was you fertilized, even when you can no longer detect the iron. The aim is to create a coherent patch, generally on the scale of about 50 to 200 square kilometers of surface seawater, which the ship can return to the center time and time again and look at the response. So basically, you're using the ocean as a test tube here. By having that SF6, which is a tracer, the label of it, you can see the changes that have gone on in the patch and compare how the biology responds to it inside the patch and compare to the control outside the patch. So I could say a lot about these experiments, but just to give you some idea about what we found in these, I mean, we see consistent changes in all 12 experiments to date. There's changes in cell size of the phytoplankton. There's an increase in the chlorophyll per cell. There's an increase in the total amount of biomass. And part of this change in cell size is related to a change in species we see. So you always see in these, to a lesser or greater extent, a shift from smaller phytoplankton through middle-sized ones to larger phytoplankton. And this ultimately has an effect not only on the food web, but also on the biogeochemistry of that water. Now, the interesting thing about this is that some of these experiments have actually been visible from satellite. So here's an experiment we ran in the Southern Ocean where you can see 42 days after addition of the iron, you can see a kind of bangle-shaped ring of elevated chlorophyll from satellite images showing that after 40 days, the addition of that iron is still having an effect by increasing the biomass. However, so if you go back to what I was talking about John Martin's hypothesis, the first part of this was, does iron addition limit phytoplankton production? And so these experiments have probably pretty much conclusively proven that. But the second tenet, and where it relates to geoengineering, is does it increase carbon sequestration in the ocean? And generally, we tend, the limited amount of observations that have been made on these voyages have shown that generally there's no significant enhancement of carbon export into the deep ocean with ion addition. So you can get the phytoplankton to grow at the surface, but you cannot significantly increase the amount that goes into the deep ocean, which is the important point of locking that carbon away from the atmosphere for timescales of 100 to 1,000 years. So, going back to the role of SOLAS, so SOLAS and SOLAS Science have really input to this whole debate and regulation around ocean fertilization as a geoengineering approach. I've told you about the basic science we've done, and this has gone forward to inform scientific summaries, for example, for policymakers, which we did for the IOC. And then it's subsequently, because of the interest in using this approach as a method for increasing carbon sequestration in the ocean and geoengineering, it's subsequently now been brought into legislation. So after a number of meetings and discussions, the London Convention, which deals with dumping in the ocean, now has an amendment which was adopted in October 2013, which basically regulates the placement of dissolved iron in the ocean, and it prohibits it totally unless it's for legitimate scientific research and has undergone a scientific risk assessment as well. So the point I'm making about this is, despite the fact that this is fundamental research that was done to try and understand just basically what makes the ecosystems in the ocean tick, that it's proved very useful both for policy and subsequently for international legislation. And so I just think I'll just probably skip over that, but I think that probably brings me around to the role of SOLAS scientists here. So this is, and it's what I really feel is kind of a bit of a dilemma for SOLAS scientists, and it's not just SOLAS, it's actually for all scientists who are connected with geoengineering. And this was brought out by a discussion session that Phil Boyd and I ran at the Open Science Conference in Kiel a few years back, where there was discussion, a quite lively discussion about the relative importance of geoengineering and negative emission technologies, and the fact that there's a growing likelihood, which has only become greater since Paris and the recent report by the IPCC, there's a growing likelihood of deployment of at least some of these techniques. And that we as SOLAS scientists have a responsibility, because we are the center of expertise in this area and the whole of the knowledge that can inform this. But on the flip side of this, we have this, of course, we have ethical concerns about this, both from on a personal level, but also on an organizational level as well, whether research organizations should be engaged in this kind of activity. And this obviously extends to intellectual independence about how scientists can be seen to be working for organizations, particularly those who are selling carbon credits. So quite a few concerns there. But really, this kind of comes to a point where it's about what needs to happen in this space is that there needs to be a safe space for researchers. So on the right-hand side of your figure there, you can see the science that SOLAS has already been involved in terms of informing this debate. And clearly, most of this has been lab-contained or field-contained. And so it's basically governed by either institutional organizations and policies, or also even national or subnational legislation in terms of health and safety and pollution and things like that. But when you move to the scale of uncontained experiments, which is really what we've been talking about here on a large scale in the ocean, there's very limited legislation out there to control this. Now, also, so what we're saying here is not only is that fundamental research scientists have a problem that there's not the legislation in place, there's the ethical issues, there's obviously the socio-economic issues, but what's needed is a broader research governance to support scientists. There's already some codes of conduct which are listed there at the bottom of your screen in terms of some of the things like the Oxford Principles that were put forward in 2011 for scientists. But ultimately what we need is an international organization that can provide that, some ground rules for research into geoengineering. So just to finish off, just to tell you where SOLAS is now. So the SOLAS Committee, after some debate, has produced a position statement on geoengineering, and it highlights those two important points I made about the fact that any decision process around around geoengineering needs to be done informed by sound and robust science, and that clearly that SOLAS has a responsibility to make a contribution to this discussion. So there'll be further development of this at our meeting next year in Sapporo, in Japan, where there's a side event and a theme session looking at geoengineering. And I'm hoping that we'll move this debate forward in terms of developing a kind of white paper about how the SOLAS community will move forward, hopefully with the recognition that in terms of externally to SOLAS, there will be some developments in terms around research governance. Thank you for your attention.
Questions for Cliff? Alco's got one here.
Thanks, Cliff. Very interesting. I'm just a bit worried about hanging this all, as this discussion is often hung on to Martin's idea that it was the iron that actually caused the CO2 drawdown, whereas if you look at the sort of the modern paleoceanographic literature, if you want, it's much more to do with biological pump activity in a very old subsurface water, probably from Pacifica, in North Atlantic air-sea exchange, and in very heavy stratification in the Southern Ocean. So, and where these, as it looks like from carbonate iron reconstructions, are making up about one-third of the problem. So that would tie in much more with what you're finding, is that actually the whole iron addition might not result in a carbon sequestration. So I think it might be worthwhile to tie in a little bit with the more modern literature on that, because there might be more support for not finding a signal.
Sure, and you're absolutely right there. You know, there is obviously other factors involved in that paleo record. That one's always given as a classic, but I could have sat here, for example, and showed you many bottle experiments, all the results from the iron fertilization experiments, the island wake experiments, where you tend to see a big tail of productivity coming off islands, which is attributed to iron. So there's many, on many different temporal and spatial scales, there's evidence of iron fertilization. But you're right, in terms of linking it to the actual export, that's where we're lacking that information.
Thanks, Cliff. Great talk. I was really interested in your point towards the end when you were saying that we need. So let me step back. I didn't quite understand. Are you sort of suggesting we need an additional new body to oversee this? Are you suggesting we can work within existing instruments that you presented at the London Convention and others? I'm just kind of interested to explore this a little bit. And I know we have a lot of governance people in the room as well, but I'm really interested in your view on what this could look like.
My view, so to address your question directly, my view is that there is that existing governance to some extent, like the London Convention, but that's not really giving the protection that scientists need in terms of that safe space to work, about that integrity and independence from other interests around net emissions and geoengineering. And I think so. I think there should be some broader arrangement. I was particularly looking towards like Future Earth, for example, to provide that in a kind of umbrella over not just marine scientists, but all scientists in terms of any engagement within geoengineering, to provide that kind of independence.
Thanks, Cliff. That was great. What I wondered about was, as a scientific problem, how will we deal, if we go ahead and have these kind of strategies, how will we deal with attribution? So if you go out and put iron in the ocean to sequester carbon, someone else goes out and does it with macronutrients, and there's carbon in the deep ocean at 2,000 meters. You say it's yours. He says it's his. Do we have a means of sort of fingerprinting those approaches so we have some unambiguous attribution?
Yeah, it's a good point, Will. I skipped the slide actually around, which I was going to mention around attribution, but clearly on the scale of what I've shown you on one of these iron experiments, it's certainly in the surface ocean, it's easy for us to do because we have the tracer added and we follow that around. But as soon as that begins to sink into the deep ocean, it becomes an issue. There's a really good example of how that already in this space around attribution is that despite the legislation in the London Convention I mentioned around iron fertilization, an experiment took place off the west coast of Canada, the Haida Gwaii, where it was just a release of iron alone I think it was really seen as basically as a benefit to the First Nations in Canada to increase their food supply through salmon stocks and everything. But because there was very limited ways of attributing anything they saw to that, it's very hard to know. That's a very productive area, that west coast, with lots of productive eddies moving through, and it's very hard to look at a satellite image like I showed you earlier for that reason and say, that's my patch, that's what I created. So that attribution, I think, is not only, it's a very difficult thing to do in the ocean, but I think it's beholden on anybody who wants to implement these techniques to actually show that they can fully attribute.
Are there any, equivalent of a marine park, except for aquaculture parks or something, where you could propose to do these experiments?
There are, but I feel you'd get an awful lot of pushback for a marine protected area to go and do one of these things.
Right, I'm saying the alternative where you would say this is a spot where it's designated for, regenerating an ocean from nothing to begin with or something like that.
I think that's probably that whole thing about regeneration is possibly a different debate here. I think that, simply that marine protected area is obviously set up to maintain maintain the ecosystem that's there, and so any perturbation of that with any addition of nutrients, for example, would change that. Even if it might be increasing the productivity, it'd be altering the ecosystem. And so I certainly feel from the New Zealand perspective, I probably would be thrown out of the room if I suggested that. So.
All right, wonderful. Thank you. Thank all the speakers from this session. Half-hour break, and then we have 2 more keynotes for the afternoon.